Good morning and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 2, that is the DER Integrated Distribution Network Modeling, and we are continuing with the power flow model of the distribution network, where we have studied the BIM model and the BFM model, and we have come to a conclusion that BFM model is a non-convex nonlinear model. So, we have to do certain relaxation or convexification of that model to make them more suitable to use for practical or real life applications. So, we will see today that which kind of relaxations we can adopt to make them feasible. So, the unbalanced distribution network power flow models are inherently non-convex and nonlinear expressions. Traditional nonlinear programming approaches often fail to converge and may stuck to the suboptimal solution if not dealt with properly. And till now, there is no good commercial solvers or solution technologies is there which can deal with this non-convex and nonlinear expressions properly and give you a good unique optimal solution. It is still not there. You can use heuristic algorithm to get the solutions, but heuristic algorithm will never converge to a single point. You run 50 or 100 times, you will get a solution. You have to take a mean out of it, then take a standard deviation out of it, and you will suggest that this is my solution with a standard deviation of that. But that is not quite feasible. And sometime if your population identification is also not good, then it may stuck to local optimal solution. So, solving the nonlinear programming is not very promising. So, for convex relaxation of such non-convex problem, generally two kinds of convex relaxation techniques are adopted. One is semi-definite programming relaxation and the second is second order cone programming relaxation. And we will see one by one that how the BFM models can be modified by incorporating this SDP and SOCP relaxations. Apart from these two, you can also use linearization, what we did for BIM as well. You can linearize the non-convex expression and replace the non-convex expression with their linear counterparts, proper linear counterparts, and then solve them and get a completely linear framework for your problem. So, the relaxation methods can be of total 3 types. One is semi-definite relaxation, which says the semi-definite relaxation is used to approximate difficult non-convex problems, particularly those having rank constraints. So, that we have in our branch flow model, we have that matrix M, which is says that rank 1 PSD matrix, we have that. So, if you have this kind of a rank constraint in any model, then you can adopt this semi-definite relaxation. Second order cone relaxation transforms certain non-convex constraints, especially quadratic equations, into second order cone constraint. So, if you have a quadratic expression in your model, that you can convert considering your SOCP relaxation. So, that also we have in your branch flow model. We have seen if you have a simplified branch flow model, we have P nm square plus Q nm square equals to V n L nm. This equation we have. So, one is used, SDP is used when you have a rank constraint, second order is used when you have a quadratic constraint. So, these two are valid for our branch flow model. So, we can adopt this semi-definite relaxation and the SOCP relaxation. Remember, these two convert your non-convex problem or non-convex nonlinear problem to a convex nonlinear problem. It never makes your problem linear. It will keep the nonlinearity, but other than if the problem looks like that, which has multiple minimum, multiple optimal solution, not optimal, local optimal solution, it will express it as a convex function, which has only one minimum point. Okay, it is never linearized the problem, just keep it in mind. And the last is the linear approximation, where they replace the non-convex expressions with their linear counterparts, which results in a convex but linear subproblem. So, that is the difference between your first two relaxation technique and the last one. So, we will start with the semi-definite relaxation. So, this is your original branch flow model, what we have seen for three-phase system. We have neglected the mutual power, and we can see this is your branch power balance equation, where you have diagonal elements only we are considering. That means SNMAA, SNMBB and SNMCC. Only we are considering this three diagonal elements, and other elements we are neglecting. So, if we take this, then this is your power balance equation, this is your voltage balance equation, you have this power relationship, and this matrix needs to be rank 1 positive semi-definite matrix. Okay. So, you have this constraint. Now, first let us check whether actually this rank 1 positive semi-definite matrix, what you are saying, that we are using the semi-definite relaxation or non-convex relaxation because we have this rank 1 positive semi-definite constraint. So, before going to that relaxation, first we have to check na, that whether this is a non-convex expression, is it a non-convex expression or not. So, for doing that, first check whether the convexity of a rank 1 PSD matrix is belongs to a non-convex set or to a convex set. We know from the linear combination theory of a convex set that a set S is convex if for any 2 point W1 and W2 there are linear or convex combination that is given by W theta, which is theta W1 plus 1 minus theta W2, also belongs under S. If this formulae or this feature holds true for any of the solution point, for any of the set, then that set is named as convex set. So, first we have to check whether that is happening or not, where theta is in between 0 and 1. So, this is your M matrix, which is a multiplication of y and y star. So, take two solution y1 and y2. Okay. So, y1 is 1 0 column matrix, y2 is 0 1 column matrix. We are taking arbitrarily two solutions. Okay. So, your W1 is y1 star. So, if you do it, you will get 1 0 0 0 0. Similarly, W2 y2 star, you will get 0 0 0 1. So, you can see for W1 you have only one row which is having non-zero component. For W2 also you have only one 0 which has non-zero, on one row which has non-zero component. That means you have only one rows in W1 and W2 which are linearly independent. So, the rank of W1 and rank of W2 is both 1. Okay? Got it? Similarly, you can check it from the determinant as well. You determine the determinant of W1 and determinant of W2, both are coming out to be 0. So, their rank can never be 2. So, their rank is here, their rank is 1. Okay? So, convex, so the set S or this matrix M, it belongs to a set where the each and every solution point has a rank of 1. Now, we have to see whether the linear combination of them is also possessing your rank 1 or not. So, now consider theta equals to 0.5 and take the linear combination of both of them, that is theta W1 plus 1 minus theta W2. So, do the multiplication and you will get W theta equals to 0.5, 0, 0, 0.5. So, take the determinant of it. So, you will get 0.25, that is not equals to 0. That means, if determinant is not equals to 0, that means your rank is equal to the number of rows. So, that means rank of that matrix is 2. So, rank of W theta is 2, and again you can see here as well that there are 2 linearly independent rows. So, though your W1 and W2 both are of rank 1, but your W theta is a rank 2 matrix. So, that means your M matrix set is a non-convex set, it is not a convex set. So, your constraint rank 1 positive semi-definite constraint imposes a non-convex constraint with the branch flow model. Hence, now we can use our semi-definite relaxation on it. So, what semi-definite relaxation says? The semi-definite relaxation says that a non-convex relations are relaxed to a convex semi-definite programming by lifting them to a higher dimensional matrix and relaxing the rank 1 constraint. That means, we will assume that this rank 1 value for this matrix is not there. We will think the rank is 2, means we are lifting it to the higher dimensional and relaxing that rank 1 constraint with a positive semi-definite constraint. Only we will consider this matrix is a positive semi-definite matrix, not with the rank 1 matrix. Okay? So, the revised problem will become your power balance, that is obviously there, you have your voltage equation, and other than having a rank 1 constraint, you have only the positive semi-definite constraint. Okay. So, this BFM SDP will yield an exact global solution. So, you will solve this problem, you will get a solution out of it, right. So, when we will say this solution is good or this solution is exact, when it will satisfy your initial condition as well, that means from where you have derived it. So, if that does not satisfy, then your relaxation is not proper, then it is not feasible. So, if your solution satisfies that rank 1 solution or rank 1 condition, that means after getting the solution you put that in that matrix and see whether you are getting your matrix to be a rank 1 or not. If it is there, then you can say that your branch flow model semi-definite programming is a exact convex relaxation. That means you are not compromising with your solution. So, for doing that you have certain consideration. So, the relaxation may or may not be exact. Some cases you will get exact solution, some cases you will not get exact solution. That means, your rank 1 constraint sometime it is satisfied, sometime it may not be satisfied. When it will be satisfied? It will be only satisfied when you have an unique solution for all the optimal cases. That means, you have an uniqueness in the optimal solution. The problem's data ensures uniqueness and convexity, the rank 1 solution must be optimal. That means, if your solution whatever you are getting, if it is an unique solution and there is no other solution possible from that problem you solved with a particular values of the parameters, then your optimal solution whatever you are getting from that problem, that will satisfy certainly your rank 1 constraint. So, for doing that, the conditions to be exact for a branch flow model for a distribution network, first the network must be of radial topology. You cannot apply this on the meshed or weakly meshed topologies. If it is a radial topology, then what will happen? In radial system, there is only one unique path from the root to each node. That means, if this is your buses and you have a substation over here, then and you have a load here, then to satisfy this load, let us say this is your SL, to satisfy this load from this substation, you have only one unique path. If it is an weakly mesh system or a mesh system, then let us say here you have another path, then your SDP relaxation will not work for this case. It will only work when you will possess a radial topology. That means there is no freedom to create high rank. That means there is no freedom to create more number of solutions from a specific parameter values. Then your non-binding upper bounds and voltage or power. That means your power flow and your voltage limits must be very high, or your solution should be like this, that it will never touch that upper limit. Okay. Obviously, your resistance to reactance ratio must be very high. That means it is only feasible for your distribution network, and the loads must not be too much reactive. That means the loads must be R dominated or resistance dominated. Mostly all these 4 conditions, if you see, they are valid for distribution network. First, distribution networks are of radial topology, that we have already seen before. Mostly the bus voltage limit whatever facing, that 1.05 per unit or 1 point per unit, depending upon your solution or your operation time or operation situation, we never allow the system to touch to that operating limit or to the upper limit or the lower limit. We always try to keep them close to the 1 per unit. So, if it is that, then this upper bounds, if it is high and if it is very far from your actual solution, then you can say this is not a bounded problem. So, this is true. Even your R by X ratio, that is obviously true for distribution network, and the loads mostly whatever we have, generally those are active power dominated load. We always want that load to be consuming more active power or running at a very high power factor, close to 1 or 0.9 or 0.95. That means your reactive power requirement is very less. So, if this 4 conditions, which is generally or physically also true, your SDP relaxation is always tight and exact. Okay. Now, come to the next relaxation part, that is called a second order cone relaxation. So, second order cone relaxation says you do not need to go with this rank and all these things, because if your system size is becoming larger, you can imagine that matrix size is also becoming larger. So, dealing with a very large matrix and then you are trying to get the rank values out of it, and then you are saying that what is the rank value, then putting that solution to that rank and getting that rank value is a difficult and a complex thing. So, SOCP relaxation is faster compared to your semi-definite relaxation, but for that we will start the relaxation with the single phase branch flow model. We will come to that, why I started with the single phase one. So, this is your single phase branch flow model, this is your active power balance, this is your reactive power balance, this is your voltage, and this is the relationship between active power flow, reactive power flow, square of voltage and square of current, right. So, this equation we have, this is a quadratic equality, right. So, in SOCP relaxation, normally this equality is converted to an inequality. That means, other than following the exact equality constraint, we will follow a less than equal to constraint for solving purpose. For solving the problem, it is easier to solve an inequality constraint compared to a equality constraint. So, this expression can be modified like this. How it is done? We will come to it. And this has a resemblance of a rotated second order cone, means it is looks like that, which is rotating with the z axis. Okay. So, if it is that so the minimal point you have only one. So, if you go through this second order cone and solve the problem, then you will get only a unique solution for your convex problem, and then you are imposing an inequality with a convex, because this already these equations are your linear, only this is your non-convex. Now you have converted that non-convex and replaced it with a convex problem or convex expression, then your overall problem has become convex. So if you solve it, then the solution you will get, that is an unique solution. Now we will see whether we can represent these equations like that, if we can represent it as a cone expression or not. Remember this is the expression for a cone. This is a second order norm or L2 norm. Okay, if you can represent an equation like this, then it will define a rotated second order cone for a any value x in the real domain and a b scalar term which are positive scalars. So we start with this expression. Okay. So expand that L2 norm and you will get root over of 2 PNM square plus 2 QNM square plus this square is less than equals to LNM plus VN. Now take square at both the side and bring the right hand side at the left hand side. So you have 4 PNM square plus 4 QNM square, then this will become LNM square plus VN square minus 2 LNM Vn, and this will become LNM square Vn square plus 2 LNM whole of negative, that is less than equals to 0. So this will get cancel out. So you have these two terms with summation of these two terms. So this is the final expression. If you take the 4 common, then this is your final expression. So we can see that the quadratic inequality actually it shows a rotated second order cone. So that means if we can represent that as a cone, so you will get only one solution if you do the minimization or maximization objective. If you solve a minimization problem with a convex, then you will get a convex solution. So you can see your entire problem has now become a convex problem. So this has revised like this, where these 3 are your linear equations and the last one is your convex relaxed or second order cone relaxed inequality. So this is called SOCP BFM, that means second order cone programming branch flow model. So how you can assure the tightness for this relaxation as well? First and foremost, obviously there should be a radial topology. There should not be any loops in the network. Second, the objective function or the problem where you have considered this model, that should have an objective which will be monotonically decreasing or increasing. That means that itself is not a non-convex thing. That has to be a convex function. If your objective function is non-convex, then with this also you cannot secure a unique solution. But if your objective function is convex and you impose this relaxed model, then you will get your relaxation will be tight. That means you will get exact solution. And again there will be no upper bound on power injections, or if it is there, that will be very high, that will not be active in any case. Okay. If you consider this, so for a radial network, if the optimization problem is feasible and the objective function is strictly increasing or decreasing, then the SOCR BFM is exact, that is the SOC constraint is tight at optimality. Now what we say that tight? That means we are solving actually this equation, right? We are actually solving this. So you are getting some solution out of it. Let us say some Vn star and Lnm star and also Pnm star and Q Nm star. These are your optimal solution. So after solving this, that is the highest chance that you will get the solution like this, because you have put the constraint that multiplication of this 2 will be lesser than equals to square plus PNM square plus QNM square. So, whatever solution you will get, that will satisfy this inequality, that is fine. But what was the actual physics of the equation? That it says that it has to be an equal. So, the tightness or the exactness only holds true, or we can say that relaxation is good one and only the solutions whatever you are getting, that will not give you a less than operation or less than result, that will always give you the equal to result. If it is giving the equal to result after solving the less than equal to expression, then you can say that your relaxation is tight or your relaxation is exact. That means we solved a convex relaxed function, but still we are getting the original solution. If it is that so, then you are good. But this relaxation is only valid for balanced network. That is why we started with the balance model. Why? Because there each phases are separated. When you have mutual coupling in the phases or among the phases, then you cannot guarantee the exactness in the SOCP relaxation. So, for unbalanced system, each phase had its own set of variables and mutual coupling, that is the off diagonal impedance term. These terms break the separability of per phase flows and makes the SOCR inexact for 3-phase unbalanced system. So, whatever this less than equal to we took, that we cannot take for if it is like this. Let us say this is your Hg square plus QNM Hg square equals to Vn H and Lnm Gg. We took this, right, or Hg, this was Hg. So, we have that equality for 3-phase system, we cannot make it less than equals to 0. If we do it, first of the things, sometime it will not solve. Second, if it also solve, it will not return back to this equal to. That means, you cannot recover your original solution from this. If you cannot recover your original solution, that means your relaxation is not proper. And if your relaxation is not proper, then you cannot do that relaxation. That means, you are violating the physics. You are obeying the maths, but you are violating the physics. And if you are violating the physics, that means that solution has no meaning in real life. So, because of this mutual coupling, at the mutual coupling component, 3-phase unbalanced network, you cannot put this SOCP relaxation. So, what is the way out for it? The first way out, either you separate the 3 phases, that means you neglect the term which has Hg. Okay. You neglect those terms, and for if you neglect all the mutual coupling, then what will become? 3 phases will become 3 separate phases. They may not be balanced. You cannot represent them as a single phase model, but the 3 phases will be completely independent of each other, and they have only these equations in their branch flow model. If it is there, then obviously you can do the SOCP relaxation, and at each phase that will hold true. Got it? Or other option is that you go for linearization process. So, generally for balanced system, we do not adopt the linear model, because that is already we have SDP relaxation, we have SOCP relaxation, so many convex relaxation techniques we have. Because if you replace a non-convex with a convex, then you are approximating some of the accuracy, but not much. But if you go for linearization, that means there is a high chance that you are deviating from your original solution. So, always we try to keep close to our global solution. So, for balanced system, you have the options of convex relaxation, but for unbalanced system, that convex relaxation scope is very limited. That is only possible when you do the separable of the phases. So, there we do the linearization of the branch flow model. With this, I end today, and today we will continue with the linearization method in the next class. Thank you.